Hi there, this is Mr. Alexander, and right now I'm going to talk to you about the chi-square goodness of fit test, which is a test of whether a sample matches a proposed distribution. So, for instance, I have found an example from our book. It says Tuscany claims that 70% of local pet owners own a dog and 30% own a cat. Sabre decides to test her claim and learns that 23 of these people he asks owns dogs, 17 own cats. This is a fairly simple example. So the hypothesis then, the null hypothesis, is just the given null distribution here. 70% of local pet owners own a dog, 30% own a cat. So the null hypothesis actually has like numbers of stuff in it. 70% of people own dogs, and 30% own cats. Like that. The alternative is usually that the distribution is just different than that. Cat and dog owners are distributed differently. So we aren't very specific in the alternative hypothesis. We have a great degree of specificity in the null hypothesis, but in the alternative hypothesis we just say, well, we don't know what it is. If it's not that, it's something else. The total sample size, if we looking at the sample here, 23 of the 40 people own dogs, 17 own cats, so the total sample size is 40. But the degrees of freedom don't actually come from that sample size. The degrees of freedom come from the number of categories minus 1. There's dog owners and there's cat owners. So that'd be 2 categories minus 1. We're dealing with 1 degree of freedom. So if the null hypothesis is true, what would our counts look like? What would the expected values? If the null is true, then we would expect how many dog owners? Well, we would just take the 70% of 40, or 0.7 times 40, we would expect 28 dog owners. And how many cat owners would we expect? Well, we would want 30% of 40, which is 0.3 times 40, or 12. Is that what we actually found in our sample? Well, let's take a look. The observed was dog owners were 23, and cat owners were 17, totaling to 40. So now if we're going to calculate the test statistic, we're going to do observed minus expected squared divided by the expected. So in this case, the observed for dogs is 23. The expected, if the null hypothesis is true, is 28 squared divided by 28 plus same thing for cat owners. So if the null hypothesis is true, we would expect 12, but we actually saw 17. Now obviously the expected and observed values are different, but that doesn't necessarily mean that the distribution isn't what we'd expect it to be. The proposed model might be still correct. It depends on this chi-square statistic. So if I do 23 minus 28, and I square it, and then I divide it by 28, plus 17 minus 12 squared divided by 12, I end up with a chi-square statistic of 2.98. Is that big enough? Well, it depends on the distribution here. So I always like to draw the chi-square statistic, remembering that the chi-square is always one-tailed test. Here's 2.98 right here. That's my test statistic. Is that far enough away from 0 to suggest that we should reject the null hypothesis? Well, we said we had 1 degree of freedom, and we're always going to assume 0.05 unless we're told otherwise. So my critical value is 3.84, which is over here. So in this case, we're not in the critical region. We would fail to reject. And we would say that the p-value is greater than 0.05. So what does that mean in context? Well, this proposed model, we wouldn't necessarily say it was correct, we just don't have evidence to say it was wrong. So for now, we believe that the null hypothesis is the best answer we have, that 70% of people are dog owners, 30% are cat owners. But the reason you're probably watching this video is to learn how to do this on the calculator, so let me show you how to do that. And unlike the chi-square test of independence, the goodness of fit test is used on the lists. So you're going to want to go to stat edit, and in list 1, you'll want to put the observed values. For us it was 23 dog owners, 17 cat owners. In list 2, you're going to want to put those expected values we calculated. 28 dog owners and 12 cat owners. Now to run the goodness of fit test on the TI-84, you're going to go to Stat, over to Tests, and it will be right under the chi-square test of independence. So just do chi-square goodness of fit test. And your observeds are in list 1 and list 2, just like we said. And we said we had 1 degree of freedom because it's the number of categories minus 1. So when we calculate that, we find a chi-square statistic of 2.98, which is exactly what I calculated by hand, with a p-value of 0.08, which is indeed greater than 0.05, with 1 degree of freedom, like I said. And also, if you're interested, the calculations are down here for the chi-square statistic. So if you actually just did this first part, 23 minus 28 squared divided by 28, that would be about 0.8928. And if you did the second one here, 17 minus 12 squared divided by 12, that's about 2.08. So it shows you the calculations as well, which is a nice way to double check, make sure you haven't screwed up the calculations. So, again, this is a great way to double check your work and to make sure that you've done things correctly. One other note is that our expected counts for the chi-square statistic are always supposed to be above 5, and in this case, they are both above 5. So I'd say everything about this test seems good, everything's valid, I'm feeling good about it. Alright, thanks for watching. We'll see you next time.